Okay, and let you, we're going to calculate what are limits using limit laws. And the limit laws are actually shown in the book. They're shown in the book in section 2.3, right at the introduction. And there are other laws that they show throughout the book, but the laws are pretty intuitive. So what I'd like to do is reinforce the laws using examples. All right, so I'll let you copy this down. Okay, so in this example, we want to compute the limit as x approaches -1 of the rational function 2x squared plus 3x plus 1 over x squared minus 2x minus 3. Now, first of all, let's ask ourselves, is this rational function defined when x equals -1? Is the rational function defined? That's
No.
right, Nicholas. That's right. Shako, no, and Nicholas, no. Because x squared, the denominator here, okay, this denominator, x squared minus 2x minus 3, if you substitute in -1 in the denominator is going to be 0. So the function's not defined at x equals -1. However, we can still take the limit of the rational function as x approaches -1. All right, so that's something that you learned from your last homework, that the function doesn't have to be defined at the value in order to take the limit. Right? Are there any questions so far? All right, great. Well, so what do you think we could do to help us in this problem? I mean, what can we do to help us determine this limit? And of course, I know that we could actually graph the rational function and observe how it behaves near x equals -1. But here we're calculating limits using limit laws, so they don't want you to use your graphing calculator to get the answer. Okay, Nicholas has a good point. Factoring. This problem is screaming to factor, and then we'll simplify. So okay, let's go ahead and do that. So okay, for our solution, we're going to factor out the numerator and factor out the denominator. No, John. In the exam, for problems maybe from, and I'd have to study like sort of the I want to say it the right way, the types of problems. I mean, I know the types of problems you had, But like in section 2.2, there were problems where you had pictures and you could just sort of graphically look at the picture and get the answer. But in section 2.3, they want you to calculate limits using limit laws. So on the exam, if you had a problem from section 2.3, I would need you to do the work that I'm showing you as of now. And I am going to be looking at work on your exams. Okay. Work is an important part of the problem. You can't get credit if you don't show proper work. That's what I'm trying to say. Because I have to see that you're understanding the concepts. Okay, so we factor the numerator, we factor the denominator, and a little note here, we do not care about the rational function when x equals -1, right? Because we're taking the limit. Now what of course happens is that the x plus 1 factors on the top and bottom simplify, leaving us then in the problem with the limit as x approaches -1 of 2x plus 1 over x minus 3. So the limit of this rational function can be simplified to the limit of this new rational function. And you notice in the work, I'm carrying the limit at every step of the problem. That's part of the work. That's part of proper notation. That's part of what I'm going to be looking for in your work. Okay. So I might be, students, they have to kind of get used to new professors, and maybe, I don't know, maybe old teachers you had didn't worry so much about proper notation and work, but I do, because it's very important for your math careers. Okay, can we take the limit now of, as x approaches -1 of 2x plus 1 over x minus 3? Can we take that limit? Yeah, there's no problem. And to take the limit, what do we do with the -1? I mean, how should we take the limit? I mean, what are we going to intuitively do? We're going to plug it in. That's right, Nicholas. And we can plug it in because this is what's called the direct substitution property. So the book gets a little bit technical, but the direct substitution property says that if you're taking the limit, okay, you're taking the limit here as x approaches -1 of 2x plus 1 over x minus 3. You're taking that limit. There's no problem that, at x equals -1 for this particular rational function, and therefore you can just substitute in -1 and you'll compute the limit to be 1/4. And you could confirm this limit. You could confirm that the limit as x approaches -1 of this rational function 2x squared plus 3x plus 1 over x squared minus 2x minus 3, you can confirm that the limit is 1/4 by then graphing it on your calculator, graphing that rational function on your calculator and seeing that it'll equal 1/4, the two-sided limit. Okay. So like, let's say, for instance, on the exam, you had a problem where you had like one try, okay? Kind of like a regular exam, right? In class, you have one try to get it right. Well, you could put in an answer, but before clicking submit, you could check to see that your answer was right. You could graphically check to see that. Okay, are there any questions on this particular problem? Okay. And I usually pause about 10 seconds just to kind of thank you. Hold on, I'm still learning names here. Thank you, Anna. So 1/4 is the answer. That's correct, John. The limit of our rational function as x approaches -1 is equal to 1/4. Okay. I'll go. Well, that's not the value of y. That's the value of the limit. But on a graph, if you graph this rational function, the y values of the rational function, okay, I see what you're saying, John. The y values here, I mean, if you think of the function here, okay, so I don't know what that hand is doing there, but if you think of the y values of this function, if you're looking at the y values, okay, I see what you're saying. So the function values are the y values. The y values will approach 1/4 as x approaches -1. Good question. Okay, let's go ahead to our next example. This was kind of a, I mean, it wasn't that hard, right? It wasn't that hard. Okay, let's think about the limit. Let's think about this limit. Let me give you a moment to copy the example down. Okay. Well, so Nicholas is suggesting the limit is 1/t, and I welcome all responses, right or wrong. Okay. The thing is, Nicholas, the limit of this function as t approaches 0 is going to have to be a number. It's going to have to be a number. Well, 1/t though is so Nicholas is suggesting it could be 1/t. But that's not a number. That's a function of t. All right. Oh, I see. The equation simplified is 1/t. Okay, now I'm going to show you something here. I'm going to show you something. So what Nicholas is doing, and so am I assuming what you're doing, Nicholas, here is you're taking the square root of t squared plus 9 and writing it as the square root of t squared plus the square root of 9. Okay, so can we do that though? Is the square root of t squared plus 9 equal to the square root of t squared plus the square root of 9? No. It would be lovely if we could do that, but we can't do that. Oh, that would make, and then, the square root of 9 would be 3, and the 3's would cancel, and the square root of t squared would be t, and t over t squared would be 1/t. But the problem is, this is not, the square root of t squared plus 9 is not equal to the square root of t squared plus the square root of 9. Okay, and that's a common mistake I've seen students make. There's a saying that when you when you take a course, you relearn the course you had before. Now, Neil's saying that this function's undefined. Well, it's undefined at t equals 0, that's for sure. So clearly we have a complicated function here. What we have to do is manipulate the function in a way that we have to rewrite the function so it's in a nicer form, so that we can take the limit. We can't take the limit right now. So here's what we're going to do. Here's what we're going to do. Let's go to the solution. We're going to actually multiply by the conjugate. Okay, so what makes this problem hard? What makes this problem hard to work with is that square root of t squared plus 9. And then there is the minus 3 there. But what I can do is I can rewrite this function. I can rewrite it. How can I rewrite it? Well, let me multiply the numerator and denominator by the square root of t squared plus 9 plus 3. Okay, this is called, this here is the conjugate square root of t squared plus 9 plus 3 is the conjugate of the square root of t squared plus 9 minus 3. What does conjugate mean? What would like conjugal relations mean? I don't know if you've heard of conjugal relations, but maybe some of you had. If it's like it's the opposite. I mean, that would be like, I have to refresh my English, but like marriage. Conjugal relations means marriage relations. So you have square root of t squared plus 9 minus 3. The conjugate would be square root of t squared plus 9 plus 3. Okay, and we're multiplying the top and the bottom of this rational function by the square root of t squared plus 9 plus 3. Now let me ask you, if when I multiply in the numerator by the square root of t squared plus 9 plus 3, why must I also multiply in the denominator by the square root of t squared plus 9 plus 3? And that's right, Nicholas, because it's 1 over 1. So it's like you're multiplying by 1. And when you multiply the rational function by 1, it's the same rational function. John, the conjugate means, okay, I see your good question here. If you have A plus B, the conjugate of A plus B would be A what? Conjugate of A plus B would be A what else? A minus B. That's right. And so it's like here, you have the minus here, and you have the plus here, and everything else stays the same. Okay? Are there any questions so far? Well, the value, like the A here would be the square root of t squared plus 9. The B here would be the 3. So I just like you're comfortable that A conjugate of A plus B is A minus B. So hey, the conjugate of square root of t squared plus 9 minus 3 should be square root of t squared plus 9 plus 3. That's what I'm saying. Now, let's see here. Let's look here. We have a, I mean, let me ask you this. If I had, let's take that conjugate idea. If I took A plus B, and let me do it this way, since we have the minus first here. If you took A minus B and multiplied that by A plus B, you have a binomial times a binomial, just like here in our problem, we have a binomial times another binomial in the numerator. What procedure do we use to multiply two binomials? And Nicholas is right, you're going to get A squared minus B squared, but how do you multiply a binomial times a binomial? Sebastian's right, you use the FOIL procedure. You use the FOIL procedure. So we're going to do the same thing in our problem here. We have to, you know, I want to say this the right way. We're rewriting our function in a friendlier way. Okay, so, okay. In step 3, I did the FOIL in the numerator. I left the denominator alone, but I did the FOIL in the numerator. Okay. And this is what I'm going to expect to see on your exam, this work. Are there any questions on the FOIL? How we got well, I can just FOIL first stands for multiply the first two terms. The square root of t squared plus 9 times the square root of t squared plus 9 is t squared plus 9. And then O is for outer. If you multiply the 3 times the square root of t squared plus 9, those are the two outer terms, you get 3 times the square root of t squared plus 9. And then for inner, and this will all be in the recording, but it should be reviewed, inner would be the inner two terms. That's the minus 3 there, and the square root of t squared plus 9, and you multiply those together, and you get the negative 3 times the square root of t squared plus 9. And then finally, the last would be the last two terms, which would be negative 3 times 3, and that gets you negative 9. Now, what nice thing happens in the numerator? I mean, we did this for a reason, right? We multiplied by the conjugate on the top and the bottom of our rational function for a reason. What nice thing happens in the numerator? They'll cancel out. The square root terms cancel out. Very good. Very good. Thank you, everyone. And so what you're left with now is t squared plus 9 minus 9 in the numerator. You still have the denominator. Oh, you're right. Ian is right. The 9's cancel out also. So you'll get to this step here then. Okay. Okay.
Hey, Emma. You need something?
So, okay, so now does something else nice happen? Does something else nice happen here? The t-squareds, we don't want to say the t-squareds cancel out. I know what you mean, Nicholas and Ian. We want to say they simplify out. The 3 times the square root of t squared plus 9 terms, they cancel out. But these simplify out to 1 and 1. And actually, you know, and so now here is our limit. Here's our new limit. I should dot my I's, right? I haven't dotted my I's. I should. One time in high school, I had 100% on an algebra test. Well, it was a trigonometry test, actually. But I lost a point because I didn't dot my I's for my sine functions. So, you know. Okay, so are we able to take the limit here as t approaches 0? We absolutely can. And we can just substitute in the 0, and you're going to get then, okay, you're going to get 1 over the square root of 9 plus 3. Yeah, the bottom didn't come out, so I'm writing it here, yeah, with my marker, John. You're going to get 1 over 3 plus 3, and that's 1 over 6. That's right. That's right. So whenever you have, yeah, thank you. Whenever you have a square root plus something, or a square root minus something, or something plus a square root, or something minus a square root, usually what you do is multiply by the conjugate. How many think that's kind of a cool limit? We did kind of a cool problem there. Yes, thank you. Neil, Nicholas, and Ian like it. Lynn says good for them. Okay. Well, you know, in calculus, Layla, you don't like it now, but I think you will. Maybe next week you might feel differently. We'll see. We'll see. But the fact is that you know, you're expanding now into calculus, and so you're going to be doing things that you've not really done before. You know, very new things. Okay, shall we go ahead, and this is a rule for, well, you know, John, I have to be careful. I don't like to say it's the rule, but generally, if you have the square root of something, the square root of a function minus a number, something like that, then, you know, multiplying by the conjugate is what you need to do. And when you get enough practice, you're going to get a feel for this. You're going to get a feel for it. Okay, let's move to our next example. So, John, yeah, what law do you use? And that sometimes you have to think. It isn't going to come right away. Like, all right, this next example, let me show you. I'll kind of, let me give you a moment to copy this example down, and then we'll talk about this example. Okay, so we want to find the limit if it exists. You notice I'm always saying if it exists. We want to find the limit as t approaches 0 of 1 over t minus t squared plus t. So this is this is a new situation. You've never computed this limit before. So we have to think of what to do. So clearly, we can't plug in 0 for t because this difference of these two rational functions is not defined at t equals 0. But I like what Nicholas said there, and I like what Ian said. I see two fractions here. I see the difference of two fractions. When we have two fractions, what do we like to do with two fractions when we have the difference or the sum of two fractions with different denominators? What do we like to do? We like to find, that's right, Kelvin, we'd like to find the common denominator and combine the fractions. So we have to do something to simplify this function. So that's what we're going to do. We're going to try it and see if it works. Okay, we're going to try it and see if it works. Okay, so, all right. So now Kelvin is right, and he's saying what Ian said. In order to find the least common denominator, the t squared plus t, I'm going to factor out a t, so I get t times t plus 1. What is the least common denominator going to be then? Between these two fractions, you have two fractions here. That's right, Sebastian. T times t plus 1. Okay. So let me go ahead then and multiply the 1 over t by t plus 1 over t plus 1, because it's the second fraction is okay. It has the common denominator. And so now we can combine the two fractions. So when you look at this, just like when you look at this in the on the screen here, what I'm showing, do you see these three like limits? I mean, I know the page that I uploaded has more work on it, but is what you see what I see, the three limits here? You know, this this step, and this step. I'm just kind of curious if that's what you see. Oh no, but you can zoom it, right? Okay, you can zoom your view so that you're okay. Never mind, never mind. Are we good so far? Excellent. Are there any questions? All right. Notice I'm carrying the limit with me. I'm carrying the limit. This is a problem where I'm computing a limit. So I have to have the limit there all the time because I'm computing a limit. Okay, well let's go ahead and simplify the numerator. If we simplify the numerator, the ones cancel out, and we're going to get the limit as t approaches 0 of t over t times t plus 1. At this stage now, are we happy? What nice thing happens here? Sure, we're happy. What would we do next? Simplify. The t's simplify. That's right, Zoe. The t's simplify into 1 over 1. And so now you can just 1 over t plus 1, you just put in the 0 and you get 1. And that's your answer. That's your limit. How many like that problem? Is this problem better than the last one? Oh, Yaki likes it. Okay. Aza, Sebastian. Okay. Okay, getting a difference of opinion. All right. Okay. All right, lots of difference of opinions here. Okay. Now, I'm almost sure this next example, thank you, Lynn, Ian, John, Nicholas, Sebastian, Aza. So this next example is going to seem a little bit different, but you're going to find it's going to be okay. May I move to the next example, or are there any questions on this one? I want to make sure I'm pacing myself well. All right. Take a look at this limit here. Thank you. What are these symbols here, these up and down symbols here? Absolute values. Okay. All right. So you've all seen absolute values. You know, the absolute value of 4 is just 4. The absolute value of negative, and this is not related to the problem, it's just, what's the absolute value of negative 4? Positive 4, okay. All right, let me give you a moment to copy this problem down, and then we'll see how to deal with it. Thank you. So I hadn't thought about it that way, Lynn and Yaki, but okay, Rodrigo, that's fine. I mean, when I think of absolute value, this is all I think of. I don't think about distance from, I mean, I'm not saying you can't interpret it, but okay, I see what you're saying. Yeah, I mean, the absolute value of -4 is 4 units away from 0. So that's right, Lynn. The absolute value of -4 is 4. Okay. So we are going to try to see if the limit exists. The limit as x approaches -6 for the rational function 2x plus 12 over absolute value plus 6. I'm sorry, 2x plus 12 over the absolute value of x plus 6. So what kind of makes this problem hard? What makes this problem different or hard? The absolute value. That's right. So if the absolute values weren't there, we'd be happy people, right? Because we know the numerator can be what? We can do what with the numerator? It can be, we can factor, and that's right, Ian, we can factor the 2 out. The numerator here is equal to 2 times x plus 6. Well, of course, this function, John notes that this function here is not defined at x equals -6, and that's true. That's true. But that doesn't mean that the limit could exist. The limit maybe exists and maybe it doesn't. But what we have to do, I mean, man, you know, that x plus 6, we almost want to simplify it with the denominator here. But we can't. We can't because the denominator has an absolute value. So we're going to have to deal with the absolute value and actually break the problem up into 2 parts. Let me show you how that works. Okay, so first thing I do is I define what the absolute value of x plus 6 means. Now, incidentally, you all might have seen this kind of thing, the absolute value of x. How many have seen this definition for the absolute value of x? Nicholas has seen it. And I would hope it's something that you would have maybe seen in pre-calculus. This is the absolute value of x function. Okay. It's 2x plus 12 Kelvin in the numerator. All right. So I mean, we could draw a picture of the absolute value of function x, but this is, it's not too hard to see that, yeah, that would be the definition of it for just a general value of x, the general function. And Nicholas is right. There's going to be an issue with the limit. So here, you're absolutely right, Nicholas. The absolute value of x plus 6 would be x plus 6 if x plus 6 is greater or equal to 0. This is analogous to the definition of the absolute value of x. So long as whatever is inside the absolute value signs is positive, and x plus 6 is what's inside the absolute value sign, so long as that's positive or 0, then, and I guess I can put a greater than or equal up here, then this is true. And if what's inside the absolute value sign, you know, the x plus 6, when it's negative, then the absolute value of x plus 6 would equal negative times the quantity of x plus 6. Of course, if x plus 6 is less than 0, then x is less than negative 6. When x plus 6 is greater than or equal to 0, then x is greater than or equal to negative 6. So to start this problem, we have to be sure we're comfortable with the first with what I wrote here in the blue circle. Are there any questions on that? All right.
So it's coming from the left.
Yes, Neil.
Negative.
Having a little trouble hearing you, Neil.
So it's coming from the left, right?
Well, no, this is a two-sided limit. The limit as x approaches negative. Oh, I see what you mean. Okay. So the original problem was the limit as, and I'll ask if somebody would, I'll ask, how do you get a big hand though? I just want my hand showing, but how do you get that big hand? Is it, oh, okay, all right, great. So let me just use my hand here. Okay. So the original problem was the limit as x approaches. So I'm not doing that. I'll ask whoever is doing that, moving the hand around, to not do that, please. I don't want to have to go back and, you know, take permissions away, right? Because I don't want to do that, because I want you to have permission so you can participate when need be. The original problem was the limit as x approaches negative 6. It was a two-sided limit. We are going to evaluate the two left-hand limits, the left-hand limit and the right-hand limit, and see if they equal each other. That's how we have to do it, because the absolute value of x plus 6 is different. The value is different. The function is different. The expression is different based on whether, you know, x is greater than negative 6 or x is less than negative 6. So now, for instance, approach x equals negative 6 from the left, then we're going to replace the absolute value of x plus 6 with the negative of x plus 6. Because we established up here in the circled piece of information that when x is less than negative 6, the absolute value of x plus 6 equals negative times the quantity x plus 6. Okay. And this allows us then to just simplify the limit. We factor 2 out of the top. The x plus 6 is simplified. And you get negative 2. You get negative 2. So Nicholas, the reason Nicholas is asking about up here, like I had x greater than or equal to negative 6 and x less than negative 6. Could have I had x greater than negative 6 and x less than or equal to negative 6? You could. I just chose to do it this way. Good question. Okay, so we get a negative 2. So the left side of the left-hand limit as x approaches -6 of this function is equal to -2. Now what we have to do is do the right-hand limit. We have to do the right-sided limit. And for that, I'll go to the next page, but I want to make sure everybody's comfortable so far. All right, very good. Well, let's go to the next page then. Well, thank you, Lynn. And Neil, you're right. The right side limit is going to be 2. You're absolutely right. And you could I mean, you know, now this is doing the math, right? But you could graphically verify this on your calculator. So for the right side limit, as x approaches -6 from the right, that's why the little plus is up there. The absolute value of x plus 6 is just x plus 6. And when you simplify that, you get a 2. And so it turns out that the left-hand limit is different from the right-hand limit, which is true because -2 is not equal to 2. And therefore, the limit does not exist. That's how you handle absolute value problems. So whenever you have an absolute value problem, an absolute value in the limit, you have to break it up into 2 parts and do a left-hand limit and a right-hand limit. All right, are there any questions at all on this? All right, I want to get one more example in before we move to section 2.4, but I do like the questions that are being asked here. And the book has an example 9 that deals with something called the greatest integer function. And you'll need to look at that for one of your, for maybe 1 or 2 of your problems from section 2.3. The greatest integer function is discussed in example 9. All right. So if are there any questions on this problem? We're trying to get away from using pictures to get our limits. I mean, we can certainly, pictures give us an intuitive feel for what the limit is, and it's a good check on our answer, but we're trying to be more formal now and actually work with actually computing limits. So what's going to happen at Puma is when the recording's done, what I'll do is when I'm done with the lecture, I'll show you where you can find the recording. Not a problem. Okay, no problem. And remind me of Puma. If you would remind me, then just give me a reminder. I wrote it down, but if I forget, just remind me. Okay, great. Well, let's go to the next problem here. So John says when a limit is undefined, does that mean the limit does not exist? That's or the limit be undefined and yet exists? No, if we don't really talk about limits being undefined. we talk about limits just not existing. Functions are undefined at certain x values or not. Functions can be undefined at certain x values. But limits, we say either the limit exists or does not exist. Okay, good question, good question. Okay, here's another interesting problem. I'll give you a moment to copy it down. Whoops, sorry. Okay, so this problem, we have the limit of the product of two functions, x squared times the sine of 1 over x. So the angle is 1 over x. Where does the problem come on this limit? Where does the problem come in? The 1 over x, that's right. So x, 1 over x is not defined at x equals 0. So the angle for that sine function is not defined at x equals 0. Okay, so let's see how we approach this kind of problem. So first thing I want to ask you is, can we say that the limit of, as x approaches 0, of x squared times the sine of 1 over x equals the product of the two limits? Okay, and I'm getting some different responses here. Intuitively, you might think that's true. And it would be true if the limits, we know the limit as x approaches 0 of x squared equals what? What's this limit going to have to equal? That first limit. That's going to equal 0 squared. So that limit, thank you, that limit exists. But the second limit, as x approaches 0 of the sine of 1 over x, that limit, does that limit exist? No, that limit does not, definitely does not exist, this DNE. Because what happens is the sine, if you graph this function on your calculator, the sine of 1 over x, I mean, maybe, let me see here, maybe I can, let me just see if I can bring it up here. Yeah, if you, let me see here. If we look at the calculator here, okay, and do sine of 1 divided by x. And mode, I got to make sure I'm in radians. I am. So we got sine of 1 over x. And then for zoom, I'll do zoom trig. I'll do choice 7. It's just a trig function here. There's the graph, okay? But, of course, we're interested near x equals 0. So let me do a zoom box. Zoom box. So for a zoom box, what you do, I don't know if you've seen this before. You've probably seen zoom in, but what I'm doing is I'm creating a window very close to 0, creating a box. I'm going to hit enter and anchor the bottom left-hand corner of the box. And then I'm going to arrow over here a little bit to the right of 0. And then I'm going to hit enter there. And it makes like, it makes a box. It just like gives me, it's like zooming in on a certain part of a graph that I want, but I have full control. How many is this their first time seeing zoom box? Anybody? All right, Joe. All right, Ian. Will? All right. Great, great. And you know, YouTube will have videos on zoom box as well. If you know, hopefully you have the idea here, but you know, YouTube will have videos if you need to refresh yourself on it or relearn it. But does it look like this sine of 1 over x? What seems to be happening to the oscillations as we approach 0 for the sine of 1 over x? What seems to be happening? It's increasing. The period is constantly changing because you got 1 over x as your angle, and the period is decreasing and decreasing, and the oscillatory behavior keeps going. It keeps like increasing, and you do not have a limit. You do not have a limit. So because of that now, let me get back to the problem itself. Okay, because of that, we can't say that the limit, hold on here. We can't say that the limit of the product of the two functions, we can't say that equals the product of the limits. It only works if both limits exist, and they do not. So we can't find the limit this way. We have to use another approach. Okay? And the approach we're going to use is something called the squeeze theorem. Something called the squeeze theorem. Okay, so, you know, but let's show kind of how the squeeze theorem would work. Finding this limit is not that hard. We first recognize that the sine of 1 over x is always between -1 and 1. No matter what x is, no matter what, you know, as x approaches 0, no matter what the angle is, 1 over x, you know, if it's, you know, the sine of whatever that angle is, and it's an angle in radians, right? So you know, if x is equal to 1,000th, 1 over 1,000th, the angle is 1,000. The sine of 1,000, that number is, you know, I don't know what quadrant it'll land in, the radian measure, but you know, it's gonna, whatever the sine of it is, it's gonna be between -1 and 1. Well, if this is the case, then if we multiply through this inequality by x squared, then -1 times x squared would have to be less than x squared times sine of 1 over x, which would be less than or equal to 1 over x squared. That absolutely would have to be true. By the way, why don't the inequalities switch? We always have to worry when we multiply through an inequality by a value about the inequalities, you know, switching. What can you tell me about x squared? What is x squared? It's always positive. That's right, Nicholas, always positive. So we are down to here. This inequality is certainly true. And what we're going to do is we're going to take the limit of the left function and the right function, okay, as x goes to 0. We note that x squared times the sine of 1 over x, which is the function we're interested in, we note that that's always between negative x squared and positive x squared for any x. But the limit of negative x squared as x approaches 0, that's going to equal 0. And the limit of positive x squared as x approaches 0, that's going to equal 0 as well. Yes, very cool. Very cool. What's that mean then? What's that mean for the limit as x approaches 0 of x squared times the sine of 1 over x? What's that mean? That's going to have to approach 0 as well. And that's, we use what's called the squeeze theorem. The squeeze theorem. Because the function we're interested in got squeezed between negative x squared and positive x squared, a left function and a right function, but the limit of those outer two functions as x approaches 0 is 0, so therefore our function has to approach 0. Absolutely amazing. All right. So this is a good, you know, now, I mean, and example 10, also, this is actually example 10 in the book that I just showed you, but they have a picture, a nice picture in figure 7 in example 10 of this function x squared times sine of 1 over x. So you might want to look at that. All right, are there any questions? Okay, good. I'll stop the recording now.